Hello everyone. In this video I will be presenting a Simulink model for a medium voltage capacitor bank automation controller. The model is based on a genuine and very typical Schweizer 487V application on an 18 megawatt, 3 stages, 6 megawatt each, 15 kV metal enclosed cap bank. In the past year or so, I've been involved in a lot of troubleshooting and improvement to some of these cap bank controller and protection applications. They all kind of look the same. Some different details here and there, depending on the specifics of the configuration and construction of the bank. But for the most part, very much the same idea all around. The most important common feature to all of them, all the one that I've been involved with, is that they are all provided with a 487V or E, 487E, mostly 487V relay, in order to consolidate both protection and automation of the bank in one device. The really cool thing about the 400 series Schweizer relays is the automation features in them. So they have two separate processors and scanning times, one dedicated to the typical run-of-the-mill protective relaying applications, and the second one, slower but separate, dedicated to the automation part of it. So for instance, the 751, most everyone is familiar with in the industry, has a 451 equivalent that is widely used for multiple feeder automation and auto sync applications. The 487 transformer differential relay has in turn three 400 series counterparts. The 487B for bus differential protection, the 487E for transformers, and this 487V, V as in voltage differential for capacitor bank applications. Although I found a bank with a 487E relay and no transformer anywhere, so it must be a matter of making all windings the same ratings, but the same idea as with a 487V. The even better part of these 400 series relays is the freeform logic used to program them. It's very straightforward, very simple. If you're familiar with typical protective relaying applications, you quickly learn and familiarize yourself with this Schweizer freeform logic programming system. The alternative could have been a PLC. I honestly have zero experience programming any PLC, Rockwell, Siemens, whatever. So for me as a power system engineer, this Schweizer functionality comes very handy. So I decided I wanted to create a model of it in Simulink, and I could argue that I'm doing this to facilitate troubleshooting and understanding of the system, but I will be lying to you. I just did it for the fun of it. If you read the relay setting file, you basically understand. After you studied it a couple of weeks max, you pretty much understand what's going on. But the result of this simulation is very neat. I did not think my computer was going to be able to run these simulations, but it held in one piece. And here we are. Some people like to follow sports. Some people like to play video games. Well, I like playing with MatLab. Very quickly, let me go through a summary description of the model before we finally jump into running some simulations. I'm trying really hard to keep this video under 20 minutes, 25 minutes top, avoid unnecessary rambling and digressions. So not every single detail of the model will be discussed in this presentation. The model consists of three main parts. First, and most importantly, the actual reason for this simulation, the controller itself. Second, a supporting, simplified power system to make the controller simulation more dynamic and realistic. And third and last, an interface dashboard to interact with both the controller and the power system. The controller model contains most of the real existing logic in the actual 487V automations I've been dealing with. I say most because there are some protections, alarms, interlocks that are either very simple and straightforward and require not much analysis at all, but instead would add more processing load to my model. So for instance, the key interlocking system, or all the myriad indication limit switches on power fuses, or all the RTDs required for this kind of application, HVAC controls and status, stuff like that. Or, on the other end of that spectrum, the more involved and frankly difficult to implement in this model, protective relaying functions. For instance, the voltage differential elements in the protection logic. Just bear in mind that all that stuff adds processing load to my machine, and my intention is to model the essential automation controller. As you can see, most of it is just a lot of timers and latches with interlocking logic. For instance, timers to delay back-to-back closing in between stages, latches to take stages out of service. Say one stage has a blown power fuse and will like to continue operating the other stages until next scheduled maintenance. Timers to block closing of a stage immediately after dropping it. Timers to block closing of additional stages if bus voltage is above certain level. And very importantly, the logic for the protection sequential trips, which I hope there is some time left at the end of this video to give it a more detailed discussion, since this is probably the most interesting and intricate part of this application. This power system model over here, very simplified power system, plays very much a supplementary role in this model. Nothing more than that. The simulation of the dynamic interactions between load variation, capacitor bank load, bank staging, and voltage variation at a common bus between utility, cap bank, and bus load. So what we have in it, first, the load, a variable load that I can raise and lower from the interface dashboard. Notice that I have left real power, megawatts, fixed, and only change via this little custom block over here, the reactive power, megabars. This whole thing is about reactive power only. Real power is a different discussion, maybe a good opportunity for another simulation involving turbine generators, wink wink. Second, we have the capacitor bank itself, 3 stages with switching elements, vacuum contacts, in reality fuse over vacuum contact, short circuit duties. These contacts being operated from the controller and well, the capacitors themselves at 6 megabars per stage. Finally, in this power model, we have a source, utility, stiff infinite bus. I set it at 750 MVA with an XR ratio equal to 15, so not an infinite bus, but stiff enough. Voltage a little bit above nominal at 14.1 kV, and feeding the system via an ideal OLTC transformer, 1-to-1 ratio, 0.75% step change, negligible losses, negligible magnetizing effects. In other words, just an ideal manually operated voltage regulator. For what reason, you may ask? Well, for the purpose of simulating different voltage automation triggers in the controller. Overall, the last part in this model is the user interface. It is kind of the front panel of a 487V relay for this application, but not really. It also includes some elements that I put in there just to facilitate my simulation interactions with the model. For instance, the load changing interface over here, or the bus demand deadband information displays over here, the OLTC quote-unquote controller interface further down here, things like that. Oh, and almost forgot, this RTD interface down here, its only purpose is to initiate a sequential trip, but it bypasses a lot of actual alarms and delays in between on the real application. So here we go, we're gonna start running. Oh, and by the way, I'm gonna be doing a lot of fast forwarding on this video because sometimes it's slow. And on the background, you're gonna even hear my machine kind of grinding through a simulation because it's, like I said, it's kind of heavy. So let's just start running that thing. You see it's compiling and it's finally running. You can see the signals coming on the left. So the first thing, what's the first thing we do? Well, we got to close the feeder breaker. There we go. And we got the feedback that, yeah, the feeder breaker is closed. Otherwise, it's not going to let you anything. It's not going to let you do anything with it. And the next thing we're going to do is we're going to start increasing. As you can tell right now, over here, all the stages are open. It's basically set on auto control. The manual control is off. We can start by setting everything on manual control, and I can just start opening and closing stages. What you can tell now, if you look at the voltage down here, you're gonna see how it goes up liter by liter as I close the stages. That's to expect, and it goes up again, and this is because it's in manual control. And basically what we're doing is we're sending the utilities right here. We're sending 15 megabars back into the utility. That's basically what we're doing. So we're gonna open everything back up. We're not gonna run it in manual. And as we open stuff, you can see that there's gonna be a close prohibit timer on each one of those stages. I'm not gonna be able to close any stage until those clear. And I'm gonna switch to automatic control. So now we are on automatic control, and what I'm gonna do, I'm gonna start increasing the load reactive power. We are at 4 megabars. We're gonna keep increasing, 4.8, 5.3, and now I should be getting one stage close sometime soon. There is a stage 1, it closes automatically. It's trying to offset the bus megawatt demand by 4500 in either direction, 4500 above or 4500 below, but it's trying to offset it and keep it as close to zero as possible between that band. So I'm gonna keep increasing my demand reactive power, and above 12 I should be getting a second stage coming on. 9, 10, 10.7, 11.2. I'm getting there. I'm getting there. There's the second stage. And there we are. We go back to a demand from the utility of about 6 kilobars. Gonna keep going all the way up to 18. And I should have stage number 3 coming on anytime soon on its own, automatically. There it is. Now what I'm gonna do is I'm gonna drop the load completely. I'm gonna reset it, and I should lose all 3 of them at once. That's what should happen. Right, so if I reset the load, back to 3.9 kilowatt, I start losing one by one. I start opening. I don't lose anything. I open the stages one by one. That's what's going on there. Little by little, it's gonna try to get back to a balance on the reactive power demand on that bus from the utility. So it's not doing it on 3. Maybe a problem that I need to look later on. It decrease. Well, I see. Yeah. Well, it's not going below the dead band. It's got to go even lower. That's what it is. I'm gonna take it even lower. 42, 47. There you go. 5.3. Now it's gonna take. I'm just gonna take that stage number 3 out. There it is. Okay, so I'm gonna reset it to whatever it is that I have at 37. So there we are. That was the automatic. We can do that now. We're gonna tag a stage number 2. We're gonna tag it out. That means stage number 3 is for whatever reason out of service. Now only 1 and 3 should come as I start increasing my reactive power load. It should skip stage number 2. I should have set a higher step setting. Now I realize. Okay, there, 13 megawatts. It should be coming. There it is. So we got those 2, and basically the demand from the utility now is about 1.1 megawatt. We're gonna leave it there. So we're running perfectly. We're gonna test a sudden e-stop. That should initiate a sequence trip, and basically it's gonna take the whole unit out of service until you clear the faulty condition associated with that sequence trip. I could do the e-stop, or I could do an increase in temperature. Either one of them is gonna have the same result. So if I just throw the e-stop, by the way, look, the e-stop is kind of funny, I know, but it should have been some sort of mushroom type e-stop push button. Simulink doesn't have that. It's just a rocker switch. That's all they had. But there it is. We're on a sequence trip right now. Stages 1 and 3, they were engaged, so they're kind of going through the close prohibited timer right now. The e-stop is thrown. It's not gonna let you. I can put it back on manual, and I can try to do everything I want. It's not gonna let me close anything. Basically, if I want to get out of that situation, I gotta basically push the e-stop out again, and then I have to reset that alarm, and everything goes back to reset. Stage 2 is still tagged out. Let's assume we just fixed it. Stage 2 is gonna be back in service. We're on manual control, and I'm gonna go back to automatic control just because it's easier on me. I'm gonna bring a couple of I'm gonna increase the load. There it is. So 2 of the stages come on. The next sequence trip fault that we can initiate is an increment in temperature, and I think it's set at around 43 degrees. That's up for discussions. I don't know if it's the same in Alaska as it is in Florida, but you know, there is a trip setting associated. There you go. You get another associated with temperature. You get another sequence trip. Same issue is going to tell you it's an RTD trip. It doesn't matter how many times I reset it. The temperature is still 44 degrees. Nothing is going to get out of that sequence trip. So you basically, you know, the sun has to set and temperature has to come down, and that's why I set this manually set temperature device over here, so I could model situations like that. Now that the temperature came down, now I can go and reset my sequence trip, and immediately all my stages are gonna come back on. I'm gonna reset my load back, and the next thing I want to do is dropping stages. By the way, simulation time, This time going on down here has nothing to do with real time. It's just simulation time. It's not real time. What's the next thing I can do? Well, the next thing I want to do is I want to play with the tap. I want to have, see, S3 is engaged. I'm going to go into manual control, and I am going to close S2. And oh, it was on close prohibit. So I'm going to close manual 2. I'm putting 8.8 megabars back into the utility, and what I'm going to assume is voltage is going to start going up. So I'm going to start raising the tap, quote unquote, manually in that, and I should have a situation right after 103% of the nominal where I shouldn't be able to bring any other stage up. So I got a stage 2 and a stage 3 on, and I got a block close at 103% of the nominal voltage. So I'm gonna try to go and close stage number 1, and let's see, I can't. It won't come on, right? And that's the purpose of that protection. The voltage is already so high, I'm gonna assume you have enough reactive power supply locally at the mill, and I'm not gonna let you close an additional station. That's what I'm doing in there, right? But I'm gonna take this a little bit forward, farther down. I'm gonna go, and this is not gonna be perfect, because what's gonna happen is I'm gonna increase it above 104.5%. It's gonna drop a stage, and in reality that should result in the voltage at the bus going down as well. That's not going to be the case in here. In here I would have to manually come and tap down that that voltage. So, but let's try it either way. I'm going to go tap up, tap up. There it is. It dropped. Oh, it did. I'm sorry. I don't know what I was saying. Yes, I do have a power system model. That's exactly why I set the power system model in place. I wanted to model exactly that situation. I'm gonna go again up and up, and there you go. It drops the voltage down again. It drops it. It basically drops a stage, and the consequence is the calculations on my power system model. Basically, the models is gonna set the voltage down. It doesn't matter what I do with the tap. Now I can regulate the tap down again, and that's what it's doing. So I'm gonna close a couple of stages back on. One, is it gonna let me close 2? In a moment it's gonna let me close a stage 2 and 2. Come on. Oh, I reacted too fast. Okay, let me close 3. There you go. I got 1 and 3. Voltage is going to be around 1.03. It's not gonna let me add anything. What I'm gonna do now is I'm gonna initiate a sequence trip based on a voltage protection. So I'm at 103.5%. I'm gonna try to take it above 106%, and when I hit that point, it should drop the stages, it should initiate a sequence trip, and it should lower the voltage that I am sensing on my capacitor bank bus. So here we are. 104, 105. I'm almost there, right? Nope. 106. Oh well, it keeps dropping things. It keeps dropping, so I'm basically fighting the capacitor bank with my own load tap changer. But there you go. As soon as everything drops, I'm not fast enough, I guess, on my clicking of the taps. There you go. We are on 106%. It basically initiated a sequence trip. It drops everything. It's not gonna let you close any stage. And there we are on a sequence trip. Nothing is gonna work. I gotta reset that sequence trip. For me to reset that sequence trip, the voltage needs to naturally come down. Naturally, no. Someone needs to do something on the load tap changer in an actual transformer somewhere. So if the tap changer is in an automatic controller, the automatic controller is gonna take care of it by itself, right? But again, it's not a full-fledged power system model of an actual mill. It's just me trying to convey that idea and doing a little bit of trickery here and there. So I am lowering my secondary tap changer. I'm gonna set it at 100% nominal, more or less. Everything clears, but you have to acknowledge as an operator that something happened. So you gotta come back in here and reset that sequence trip. Now the next thing I'm gonna do, I'm gonna close those stages on back again, and I'm gonna see if I can do it fast enough. And I'm gonna take it all the way up to 108, and it's the same thing if I was to take it all the way down to 85% on an under voltage element. What it's gonna do is gonna trip. If you get to 108 volts and you already drop all your stages and you're still above 108, something is really wrong, and it has nothing to do with the capacitor bank. So the capacitor bank relay is gonna go like, I gotta protect the capacitor bank, so I'm just gonna drop the whole thing. And the same thing at 85% on the voltage, right? So let's see if I can get there fast enough. I don't think I can, but okay, there you go. That would have been a different setup in the simulation. So I'm at 109%. It dropped the breaker. It's on a sequence trip. Is basically above 108%. It dropped all the stages. So what do I need to do now? Well, I need to go through a whole resetting of the unit, right? Well, number one thing that needs to happen is something happened on the power system beyond the capacitor bank, and the voltage came down. Once the voltage comes down below that 108 set point, let's assume that they have everything in place to automatically bring the voltage down for whatever reason. Maybe they drop a lot of load and they didn't realize some generator somewhere was still outputting an unbelievable amount of reactive power, or the load tap changer in the utility transformer is not in auto control, it's left in manual for one reason or another. Who knows? It's beyond the capacitor bank protection scheme. So the voltage came down. I can go and reset my relay. Is it gonna reset? Yeah. And then I gotta close my breaker back again. And then if I put it in auto, let's assume we left. By the way, let's assume we left the load on that bus. Let's assume we left it high. Somehow it was still demanding that amount, say 14 megawatts. So I'm gonna switch from manual to auto, and it should start picking everything up immediately. There you go. So it needs to pick a stage 2 because it's still above that. There you go. And now the demand from the utility is only almost 2200 kilowatts, 2.2 megawatts. So it's within the dead band. It's not gonna bring a stage 3 on. It's a compromise amount, I guess, you gotta come up with. And there you are. We're offsetting about 12 megawatts from a 14.7 megawatt on the bus. I want to show you and see if it refreshes everything. It takes a while to refresh all the signals during the whole simulation, but you can treat these plots as a sequential event report if you think about it.